Something? Not much? Did I say something more? No? Okay. Something? Yeah, I will speak louder, I guess. Yes, yes.
Welcome to the afternoon section. And because Friedrich is not well, so he is not currently present in the conference. So I will be chairing this section. And this section will have 3 papers on mixed set and parallel set. And the first paper will be given by Ilario Banasila. So welcome.
Thank you. So, can you hear me properly? Yes, I guess. Okay. Whoops. Okay, so, well, anyway, so this is a joint work with Maria Luisa Bonet and Massimo Lauria. And that's it. Okay. Okay, so joint work with Maria Luisa Bonet and Massimo Lauria. And it's a work about Max-Sat resolution and how to use redundancy rules, somehow inspired by the ones by SAT in the context of Max-Sat resolution. So as a haiku, if we want, this work can be phrased in this way. Redundancy rules for SAT can be added to Max-Sat resolution, and instead of using unique propagation, you can use inclusion. This might mean something to you or not, but hopefully at the end of this talk, this might mean more than at the beginning. So, okay, so the first 2 slides are about redundancy. We already heard about redundancy quite a bit in this conference. Let me quickly recap some small things, and then I will go to the core of what I want to talk about. So we have a set of clauses, S and a clause C that we want to add. And if this set of clauses and the same set when you add this clause are equisatisfiable, then we could say that we can assume this clause without to be true without loss of generality. And this we could say that the clause is redundant with respect to this set of clauses. And of course, this without loss of generality reasoning is something that we do all the time in mathematical reasoning, but is also very relevant to SAT solvers proofs. In pre-processing, in-processing techniques exploit this. And also can be seen as a way to exploit some sort of symmetries of the problem. Well, it's between quotes, like without loss of generality reasoning, let's say. Well, when you say without loss of generality, there is always hidden some sort of symmetry because you exclude some claims. Sorry, say it again. Oh, yes, with Y, sorry. There might be typos, okay. sorry. Yes, sorry. Okay, the first typo is, okay, sorry. Okay. Okay, so redundant clauses. So of course, a clause that is a logical consequence of S is redundant, but we're interested in clauses that are not logical implications. So one way to check if a clause is redundant is if this property holds, if okay, this is very difficult. Okay, if there exists some assignment sigma such that when you restrict the set of clauses S with the negation of your clause, you get some bunch of clauses. If this semantically implies the set S union the clause restricted by this assignment sigma, then you could be sure that the clause C redundant with respect to S. So what is the interesting case to check? So if there was a total assignment, so we need to check that S and S union C are equi-satisfiable. So if there was a total assignment alpha that was satisfying S but not C, then alpha was extending not C, and so alpha was satisfying the left-hand side as restricted by C bar. And so by this semantical implication, then alpha composed by sigma will satisfy S union C. So if we have this semantic property, then we are sure that the clause C is redundant. Yes. That one is satisfiable if and only if the other one is satisfiable. Yes, yes. Yes, please interrupt me in any moment. Okay. Okay, so of course, semantic implication is not efficiently checkable. So instead of it, people have considered unit propagation as an efficiently computable proxy. You might, or well, probably everybody of you will know what is unit propagation, but I will not define it because I will not use it. I will use something weaker that is even weaker, like just inclusion. So if the left-hand side includes the right-hand side, of course, there is a semantic implication. And the point of this talk is that if you use inclusion, already the system that you might get using some sort of rule based on this are quite strong, and they might be used for maxat. So this is at the same time some sort of recap of the jargon of the names of these redundancy rules in the context of SAT, but I will do it in the context of this adapted rule that we define in this paper. So the only difference with the normal rules for SAT is that here I have an inclusion. In the normal rules of redundancy for SAT, there is a unit propagation, right? But I will use the setting of the inclusion. So the general framework is that, okay, we have a clause C, and this might be something redundant with respect of a multiset of clauses S if there is a sigma such that this thing hold. And now, depending on what the sigma we allowed, we have different possible strengths. So the terminology inclusion refers to the fact that here we are using the inclusion and not unit propagation. If the name of the rules are exactly the one that you might have been seen in the context of redundancy for SAT, where you have unit propagation, in this case, it will be substitution redundant. Since there is inclusion, it's inclusion substitution redundant. So this is the most general one that we consider. So if sigma is a substitution. A slightly weaker one is that if sigma is a partial assignment, there is a lot of terminology that is not always, probably is not that useful for remembering these rules, but okay, so the rules are listed in the strongest, slightly weaker, and so on. So the third one is subset propagation redundance. So we have an assignment, and now we restrict further to have it the same of domain of C bar. Literal propagation redundance, or also RAT. If sigma is an assignment with the same domain, but now you change only one variable. In SPR, you are allowed to change more than one variable. And blocked closed, you might know what it is. So this is just a very strange formulation of what is a block clause, just to say it fits to the framework. Okay, so if you have never seen these rules, just focus on the first one, substitution, or any of these that you find nice, like propagation redundant. The framework is the same for all the rules. The terminology is not helping that much, but okay, so these are the rules. And of course, one could add these rules to resolutions. No, you have a resolution proof. At some point, you have a bunch of clauses, and you might want to add the clause that is redundant with respect to this bunch of clauses. So you might have a resolution plus ISR or plus SR plus all these systems. Okay, so remarks. If we allow new variables, all these redundancy rules are very strong. Even the weakest one that is blocked clause, they all collapse to extended resolution. So even if I'm not saying explicitly, from now on, I will always consider these rules when we disable this thing. We don't allow new variables, because otherwise it's extended resolution. It's very strong. And we want to see what is able to do with these rules without new variables. Now, these rules that I defined, they are ISR, IPR, and so on. They are already implicit in this paper by Sam and Neil, especially ISPR. It's a fragment of SPR that is already enough to do some quite strong reasoning. In particular, resolution, when you add this redundancy reasoning, without new variables is quite strong. You can prove efficiently the pigeonhole, you can refute efficiently the pigeonhole principle, bit pigeonhole principle, citing, you can undo xorifications, you can prove efficiently key coloring formulas, and lifting are all easy. In this paper, it's not stating for ISPR, but you only use inclusion, so it's in this system. Okay, so what about hardness results? So we have exponential lower bounds only up to the level of LPR, again, Verstappen, and also a system that I didn't call that is weaker than SPR, which is called SBC, subset block clauses. Of course, all of this system without new variables. Questions so far? Was I too quick or? Okay, so yes. Right, so that will make the system stronger. In this setting, we didn't consider the system with deletions. The system that I will define in a couple of slides has some sort of deletion, but is not the type of deletion that you have in your paper on an arbitrary deletion of clauses. More questions? Okay, a couple of open problems about this that I find interesting. So the first one is, well, find a formula that is hard for exponentially hard for resolution plus this symmetry reasoning. Of course, without new variables, otherwise I will be asking a lower bound for extended Frege. And the other one is, since now we define the system with inclusion and the usual one are with unit propagation, does the unit propagation really give an advantage over inclusion if for instance, if we are over SR, you're allowed to use symmetries? And okay, so these are two kind of natural questions that arise from this framework. And now, okay, so this is about the redundancy for SAT, and now I want to say something about MaxSAT and MaxSAT resolution and how to use this in that context. So the first thing to recap, okay, MaxSAT. So we have a proof system for MaxSAT that can show lower bounds on the cost of MaxSAT instances, the minimum number of clauses needed.
Hilario?
Yes.
Okay, if you go, but this thing you said about unit propagation, so stupid question, but why can't you, if unit propagation gives you anything,
yes,
why can't you just sort of, I mean, that's just a trivial resolution. Like, why can't you just add that sort of the derivation you need before and unrestrict it, and now you do inclusion? So why isn't it sort of the same because you just do the proofs you need in advance? But that doesn't work.
In what context are we talking about? In the context of SAT or MaxSAT? What context are you thinking about?
Whatever context. I mean,
like resolutions. Okay, so resolutions.
Because if I always thought of this as set inclusion as almost just, you know, a simplifying assumption with no real implications, but maybe that's not true. Because I think, again, if I want something to, if I can derive a clause by unit propagation, then I could sort of.
I mean, the unit propagation is not part of your proof, right? So, I mean, the unit propagation here, so you're saying, okay, perhaps the clauses that I will use unit propagation you want to derive it before in the resolution proof?
Yeah.
Can you always do that? I'm not sure.
Good question. That's
No,
I guess that's my question.
Oh, I don't think so. I'm not sure. I have to think about it. I don't think it's obvious, no? Perhaps okay, so that could be seen as the question. So if you can actually do this, I don't see how. For sure, in the context of Maxat, using unit derivation breaks things. So if you use inclusion, the cost is preserved and so on. But I will come to that in a couple of slides. Thanks. Okay. Okay, so in the context of Maxat, we have the cost, which is the number of clauses that we falsify, the minimum number of clauses that we falsify in that set over all possible assignments. And okay, so without loss of generality reasoning in the context of Maxat is implemented in great generality in very PB, which is focused on proof logging, and it's extremely powerful, as we saw in Tappen's talk. In this work, we somehow take an approach of, okay, we want to use the minimal amount of reasoning on top of Maxat resolution, which is kind of the base system. But we want to see how powerful is this reasoning. So we want to somehow have a simple variation of SAT redundancy rules using inclusion instead of unit propagation, and check if this makes the Maxat resolution quite strong enough to refute a lot of basic benchmark for checking that the system is good. So Maxat, so in the context of SAT, the base system will be resolution, and then we add this redundancy. In this context, we have we could consider Maxat resolution, and then we add redundancy rules. So Maxat resolution is just as an input, you are given a set of clauses or a multi-set of clauses, and a proof is just a certification of that the cost is at least some number k, is a sequence of multi-sets. You start with the first multi-sets, and each multi-set, and you end with the last one with k copies of the false, and you go from one to the next, either applying a symmetric cut or a symmetric split. So this is Maxat resolution. And of course, we could add reasoning symmetry without loss of generality reasoning in this way. So if we have a clause C that is ISR with respect to the multi-set we are in, we can add it. Or if it was redundant, if we removed it, then we can remove it. So in some sense, answering to your question, Neil, is this is some sort of deletion is allowed, but it's you only delete when you already know it's redundant, so it's not a generalized deletion. Okay, so another comment is that adding these rules, of course, you could have add IPR, ISPR, whatever other redundancy rules you want. It gives a different system. And now adding these rules will also in the context of weighted and partial Maxat, also with negative weights, which is another way to say Shirali-Adams or unary Shirali-Adams. Okay, so let me check why the soundness. So the soundness means that the cost of each multi-sets along the proofs of this system is preserved. So in particular, this means that if we have a clause that is redundant with respect to a multi-set of clauses, then the cost is the same, is preserved. So why is that? So one direction is obvious. The cost of S is always smaller than the cost of S union C. To prove that inequality, let's say that K is the cost of C of S, and beta is a total assignment that realizes this cost. So now if this assignment satisfies the clause, we are done. So if it doesn't satisfy, then it extends the negation of C. And now by assumption, since it was ISR, there is a substitution such that this inclusion hold. And now you just restrict the inclusion by beta and you get this other inclusion. And now since this was an inclusion and you take the size, then it's fine. You get an inequality about the size. If this was a unit propagation, then you could not infer this inequality. And so basically, yeah, that's it. So this is why the redundancy work, and this gives an upper bound of the cost of S union C of K. Okay, so this is the soundness of the system. So so far I just described the system, and now the rest of the slides are just, okay, now we have this system. Perhaps it's a good candidate to test our standard procedure to prove lower bounds against the proof systems. And so this is saying, okay, obvious choices fail, like the pigeonhole principle. You can always certify efficiently the cost of some hard tautology, like the pigeonhole principle, parity, you can undo xorification, and also the system is able to capture simple branch and bound procedures. Okay, so the first one, okay, the pigeonhole principle, it's easy. What does it mean? So pigeonhole principle, just the usual propositional encoding of the pigeonhole principle. We have m pigeons and n holes, so it's not minimally unsatisfiable. And now the claim is that there is a polynomial size derivation in Max-Out resolution plus this redundancy, ISR, showing that the cost is at least m minus n. This is optimal. So what does it mean? So you have the pigeonhole principle. Each clause is present only once. And when you use it, you need to remove it from your database. You consume it. So the proof sketch is something that you could imagine. So it's just we go from the pigeonhole principle with m pigeon and n holes. We remove one pigeon and one hole. We repeat this process m minus n times, and then at the end, the pigeonhole principle with 0 holes is just n minus n copies of the false. So we are done. So the tricky part is to go from the pigeonhole principle n to the one with one pigeon less and one hole less. And basically this is done using this redundancy rule to enforce one by one all the pigeons of index below m to not fly to the hole n. This is similar to an argument in this paper by Holle, Kiesel, and Beer, but it's adapted to the context of substitution rules. So in particular, you cannot reuse for free an axiom several times. In particular, okay, a couple of open questions. So let's start with the second one. So this type of, so in Bastappen, there is a upper bound, a polynomial upper bound on the proofs of pigeonhole principle n plus 1n. So this is easy to refute in resolution plus ISPR. We were not able to do it for this type of pigeonhole principle in that system in the context of Max-Out resolution, because in that argument, basically, some axiom are used several times. So one open question is if the system, the weaker system, Max-Out resolution plus ISPR, is able to certify the cost. But the most interesting question is, even in resolution, is if the graph pigeonhole principle is easy to refute. So graph pigeonhole principle is just a pigeonhole principle where each pigeon is forbidden to fly to some hole, so some variables are set to 0. And so this, if the graph doesn't have symmetries like an expander, it's not clear if it is easy to refute in resolution plus these strong systems. And why is this? So we are usually, in proof systems, we are usually given for granted that they are closed under restrictions. So this is not the case in this context. So if you have a proof and you're restricted by some assignment, then it's not anymore a valid proof. So that's why this open problem makes sense, because usually if you have a proof of the pigeonhole principle, you're restricted, you have a proof. I mean, a way to refute the graph pigeonhole principle cannot be easier than the proof of the pigeonhole principle. So, okay, so parity. Parity is another example. So now parity is a propositional coding of, you have a complete graph with n is odd, and you have a perfect matching, which is of course not possible. So the other result is saying, okay, we can also certify in Max-Out resolution plus ISR that the cost is at least 1, that this is unsatisfiable. And the, well, interesting thing is that here the proof uses the axioms only once. Otherwise, you could just use a resolution proof. So the strategy is to start with clauses of parity and deduce from it the clauses of parity with 2 vertices less. And basically, it's just to use the ISR rule to match two elements, and that's it. So, okay, as a consequence, neither Shirley-Adams nor sum of squares can simulate this system. So this is another somehow hint that this system is quite strong. Okay, so now open problem. Again, in this paper by Bass and Tappen, they prove the upper bound in ISPR. So we were not able to do that for the same reason. Some axioms are used several times. It will be interesting to see if this could be avoided. Another thing, another check, okay, you cannot make things harder if you use xorification. In this system, you can undo xorification, also in the context of MaxSat. Xorification is just a standard trick to make a formula harder. You substitute variables with XOR of m new variables, and then you expand it again in CNF form. So basically, the result is saying, okay, if you start with a formula that is easy for MaxSat resolution, so in MaxSat resolution, it's easy to certify that the cost is at least k. Then if you use MaxSat resolution plus ISPR now, the weaker system, you can also certify that the cost is at least k in the same, well, in the size polynomial in the original one and the number of clauses. And here it's even simpler. The idea is just to remove all the symmetries at the beginning and then do the original derivation. And this is doable in this system ISPR. Last, we showed that, okay, this system is able to simulate some plain branch and bound procedures, in particular, and I will recall what is a branch and bound procedure in a moment. So given a branch and bound procedure for MaxSat, so it's a decision tree that certifies that the cost is equal to some value k. Then there is a MaxSat resolution plus IPR proof of length polynomial in the size of the associated tree. So basically, the basic branch and bound procedure explores the pace of all possible assignments in a depth-first way, and at every node there is an upper bound and a lower bound. The upper bound is the cost of the best solution found so far. The lower bound is the number of falsified clauses, and at the beginning, the upper bound is the number of clauses, the lower bound is 0. And at each node, the algorithm compares the lower bound and the upper bound. And if the lower bound is larger than upper bound, then we already know we are exploring some branches that are not optimal, so we don't know that. And in the other case, you instantiate more variables and continue the exploration. So basically, this basic branch and bound procedure is certifiable in this system. Okay, so let me conclude with some recap. So hopefully now the haiku makes more sense, hopefully. And just this is a recap of the open questions that I mentioned so far. So ordered in the as interested I found it. So the first one that I want to reiterate is it will be very interesting, I think, to have a formula that we exponentially hard for resolution plus SR without new variables, of course. And then the other one that I find very interesting is the graph pigeonhole principle, if it is easy or not to refute in resolution plus this redundancy reasoning. And then the others are slightly more technical. And the last one is if these redundancy rules could be able to simulate more sophisticated branch and bound algorithms. So that's everything I wanted to say. Thank you very much. Well, you could add it to Shirley-Adams. You could say Shirley-Adams with redundancy. Is that what you were asking? Yes. But it's
where does the redundancy? How do you apply redundancy rules in Shirley?
So it will be like so Shirley-Adams. You have this algebraic expression that you need to check is equal to -1. So you need to expand the sums. So you say, okay, I expanded this up to this moment, but with respect to that sum, I could add this clause that is redundant. So it will be dependent on the way how you expand the sums. It's a bit ugly, perhaps.
Okay.
Other questions? If not, let's move on to our next talk.
Thank you.
Our next speaker will be Furong Ye, and
Yes. Can you hear me?
Yes.
Yes, great. Thanks. Okay, then may I start? Okay, then I will just start. Hello, everyone. So I'm Fu Zongye. At first, I'm sorry that we could not attend this conference in person this year because of the visa issue. And our first author, Chu Yi, because of some personal issues, she could not attend either. So I will present this work today. Our work is about enhancing MaxSet local search solver via a unified soft clause weighting scheme. And the first is about the problem, but I believe I can just skip these slides because I believe everyone in this conference understands what MaxSet is working on. So, and we are working on incomplete methods in this paper. In practice, we apply local search to solve MaxSet problem. And for local search, actually, the whole search space is formed as a network. And in this network, each node denotes a solution for the problem. And a local search usually starts with an initial solution. After that, it will iteratively moves from one solution to another one. And these moves will be guided by some strategies. In this work, we use a score function, which I will explain later. And the key issue is to use this score function to escape from local optimal. And nowadays, for the MaxSet problems, most of recent local search work we can see is built based on the satellite framework. So I took these slides from this pseudocode from satellite paper to explain how the whole local search procedure works. So in the very beginning, the local search will start with an initial complete assignment. So it starts with an initial solution. And each variable will be evaluated based on a score function. So a positive score indicates that by flipping the value of this variable can lead into a progress regarding the weights. And if there exists no score function, no variables of which scores is positive, it means that currently the algorithm is trapped into a local optimal. And in this case, the weights of each variables will be updated by the weighting scheme. So here the weights in the weight scheme will be different from the weights of the variables in the problem. And after that, the greedy strategy will be applied to select a variable with the highest score. As a note here, the score is the decrease of the total penalty weights of falsified clauses. And when we use the weighting scheme to calculate the scores. And for to explain our work better, I will introduce the existing work first. So a lot is the existing work such as satellite, after the version of it and the bandmax. It will initialize the weight of each clauses like this. So for each hard clause, it will be initialized as 1. And for each soft ones, it will be initialized by its original weight in the problem. And when the algorithm is trapped into the local optimal, with the probability of 1 minus SP, each falsified hard clauses weight will be increased by a factor h inc. And for the soft ones, it will increase by 1. And we set a threshold for soft ones. And also there will be a probability of smoothing clauses weight, so they will be decreased by the same factor. And for this method, we can see that the hard clauses and the soft clauses are dealt with different strategies. And usually the method obtains best in heavy hard clause weights. And later, I think the solver NUWLS was the state of art 2 or 3 years ago. And it updates the previous introduced method by replacing the initialized soft clauses by a normalized value. So here the initial weights of soft clauses will be initialized with the normalized factor. So here this average value is the average of all the soft clauses weights, and this S is the parameter. It's I think it's trained based on the max set competition instances. And in this solver, the local search algorithm will be embedded with a restart strategy. So at the certain condition, the local search will be restarted. So all these weights will be reinitialized. So in this case, if there is no feasible solution was obtained in the last round, the soft weight will be initialized by 1. And in the update phase, so when the algorithm is chopped into local optimal, differently from the previous satellite work. So here the difference is that the incremental factor of soft clauses weight is not 1 anymore. So now it's replaced by a factor as RNC. And just thinking about this method, we think that based on this weighting scheme, the local search space is kind of blindly altered because we increase or decrease the weights of each clauses, and at one point we have no idea how it looks like anymore. Because by adding this parameter, by adding these factors, the relationship among soft clauses weights and also the relation between hard and soft clauses will be completely altered at one point. Then it will be completely disrupted. So we thought about the challenges, how if we continue using this weighting scheme, what challenges we may face with. So the first one is how to deal with hard clauses and soft clauses differently, because we usually have pairs in satisfying hard clauses first, such that we can work on feasible solutions. And the other one is about threshold. So this is mainly about the parameters, because if we have one clauses that has been first all the time, then its weight will be just increased automatically all the time. At one point, if this value would be too large, then the algorithm cannot look up the other clauses anymore. And the last topic is about smart choice. So it's like how to select clauses for weighting adjustment. This will significantly affect the performance of the local search. So by thinking about these challenges, we proposed in this work a unified soft clauses weighting scheme. So if we look at this initialized phase of NUWLS, we could see that even the initialized weights of soft clauses is normalized by this is the average of the soft weights of the problem itself. There is also an introduced parameter S. So this S is trained based on the max set competition problem instances. However, it's really how to say, it's if we apply this solver to the others to a problem instance that is not in the set max set competition, probably this is not a good choice. So in our new weighting scheme, we change the initial phases by assigning the soft clauses weights starting from 0. So in the beginning, the hard clauses will be with a higher weights. And in the update phase, we recapping this strategy in your WRS, we could see there are many parameters introduced. And in our method, we will work in this. So if we are being trapped into a local optimal there in which the solution is infeasible, we will just only increase the weights of hard clauses by 1. And if it's trapped into a local optimal in which the solution is feasible, we will update the weights of soft clauses in this way. So the soft clauses weight will be k times the original weight of C divided by the average of all the soft clauses. And in this case, the right part is represents the relationship of the one clauses weight compared to the other soft clauses weight in the program itself. And this K is the number of feasible local optimal that has been visited so far. So in this case, we could see that our new weighting scheme obtains fewer predefined parameters. Because in these 2 steps, you can see that there's no parameters need to be tuned. And the second, because we adjust the soft weights, soft clauses weights by a linear scale factor. So this relationship among all these the weights of soft clauses will remain the same during the local search process. And we exempt this, our method, like independently just run the local search using our new weighting scheme compared to some previous state-of-art solvers, local search solvers. We could see that because in the competition benchmark set in the past 6 years, our method can obtain better result compared to other local search solvers. And yeah, we also know that in the competition, the best solvers are usually hybrid solvers. So those hybrid solvers will be embedded with a local search solver and a complete solver. So we just replace the local search solver by using our new weighting scheme, and the obtained result is also better than the other previous methods across all the benchmark sets. And this is just a recap on the results of the incomplete track in the MaxSet evaluation 2023. And our method is this U.SWC. You can see that, yeah, actually we won the competition in 2023. So the result is the best. So here comes to our conclusions. So the conclusion is quite clear. So just like our unified soft clauses weighting scheme is a useful strategy. More and it obtains fewer parameters. So it's more even though now we cannot give much like we cannot give any theoretical result, but it's just open more opportunities for us to understand how to adjust these weighting schemes better. And in the end, we also see that in the experimental results that the strategy can provide quite competitive results. And in the future, we would like to explore better strategy of dealing with hard and soft clauses specifically, because in this in our proposed weighting scheme, we just we treat hard and soft clauses differently, and we have a unified operation on all the soft clauses. So we do not just, when we are trapped into a local optimal, we do not just adjust the weights of one or multiple particular soft clause access weights. We will just tune them uniform. So in the future, we would like to explore more opportunities in this method. And also, we would like to apply this weighting scheme to the other optimization problems, such as WBO and max XMT, which in this domain, in which domains they also apply similar local search methods. So that's my talk. Thanks.
Thank you. We have plenty of time for questions. Any questions?
I'll sort of protect myself from a question I'll get otherwise and ask, why didn't you send this to the evaluation?
Sorry?
The Maxat evaluation. Why didn't you send this to the Maxat evaluation?
I think
This
this
year.
has been this year. I'm sorry, I'm not sure because I'm not the main contributor here. I think I think at least for some method it has been sent last year, but this year because Chuyi she has some personal issues, so she didn't have much energy to join the competition this year. That's the key issue.
All right.
Yeah, sorry for that.
I hope to see it in the future.
Yeah, of course, of course.
Other questions? I have a question. Can you give an intuition why your method can improve the previous work? The
Okay.
intuitive how this works?
Yeah, sure. Yeah, actually, we are still thinking about like we see the better result in this work, and we are also trying to give a how to say a well-framed explanation, but we're still working on that. But here, just a few thoughts like why this may work better. So at first we compared it to, so in this slide, we compared our method to NUWS first. So for this initialized phase. So the previous work, it will be the software classes will always be initialized with original weights or a different, or like here the or normalized value, but the hard classes, it will be 1. So there is kind of significant difference between these two kinds of clauses. And in this case, we just do it like 1, 0. So they are kind of in a how to say similar scale. So, but in the future, we will explore more how to deal with these two kinds of hard and soft clauses differently. And the different one is like previously we treat hard clauses and soft clauses differently. So we use different incremental factor for hard ones and soft ones. And you can see that for the soft ones, it's always set a threshold. And this threshold is usually obtained by a tuning method. So it could be set as 100 or 1000, but usually when we want to make sure that our solve obtains a general good performance, this value will be fine-tuned for some particular instances, but it could be bad for some other instances, we don't know. But in our method here, we just tune these soft clauses. We do not just tune particular ones. So we kind of maintaining their ratio relationship. So for example, there are two soft clauses. One's weight is twice larger than the other one. Then after this tuning, like after 2 rounds or 5 rounds, this relationship will remain the same. So we do not disrupt relationship among soft clauses, but we just use a scale factor. Then it can be helpful to help the local search to escape from the local optimal. That's the only thing we do. Actually, we also have done additional experiment to try to see if we do not just maintain the ratio relationship, we maintain the order relationship. So we just plus something every time. So the order of this soft clauses weights will remain the same, but their ratio relationship will be somehow disrupted during the optimization process. But in that experiment, we could not obtain good results, and we found this way is a good strategy. We don't know why, but in the future we will explore more. So here are just a few thoughts, but yeah, we're happy to discuss more by email or in the future events.
Thank you.
Yeah, thank you.
Other questions? Okay, if not, let's move on to our third talk.
Yeah, thanks. Now I will stop
Thank
sharing.
you. The third talk will be given by Yoichiro Aida, and he will give us the talk about parallel cloud sharing strategy based on graph structures.
Can you hear me? Okay. Thank you for the time. And I'm Uchiro Ida from the University of Tokyo. Today, I'm going to introduce our research aiming at improving the closed sharing method for the CDCL type parallel search solvers. Namely, the parallel closed sharing strategy based on the graph structure of the search programs. Thank you. So here's the outline. And as an introduction, I'm going to touch some backgrounds. The search program, the input of the search program is usually given by the format of CNF. And when I say search program in this presentation, that means an application programs. Application programs are converted from the various real-world programs, industry instances like the formal verification or theorem proofs. And also, my presentation is based on the CDCL type search solvers. In the CDCL procedure, learned close or learning is one of the important elements for the efficient search problem solving. And in the learning, we assume that one of the most important technique in the learning is the task to determine which clause to maintain or which clause to delete. That is because modern search solver intended to encounter conflict aggressively. So the solver easily obtain millions of learned clauses, and it is impractical to maintain all of them. So solver need to decide which to keep and which to delete. For that, clause evaluation metrics are widely used, and particularly the size or the activity or literal block distance are widely used. And particularly literal block distance, we use LBD as our baseline because LBD has been widely used in many solvers. And also, it is sometimes used not just for the clause evaluation, but also for other heuristics. Parallelization of the solver, Parallelization of the solver is another important technique. And in this presentation, we use portfolio type parallel search solvers. And for the portfolio type parallel search solvers, the diversification strategy is important for the efficiency of the parallelization. And so each worker are expected to and should do the different searches for the efficient portfolio type parallel search solving. A search problem is sometimes represented by the graph. And in this presentation, we use variable incidence graph, VIG. In VIG, node represent a variable, and edge exists between variables if a clause exists that contains the variables of each edge. So for example, in this, when we have this CNF, this can be converted this kind of indirect weighted graph. So that's the background. And moving to the motivation and key ideas. So this research aims at improving the clause sharing method in the parallel search solvers. For that, currently LBD is widely used for to select the clauses to share. And we say that LBD is a search dependent metric. What I mean search dependent is that value, activities also, but these values are these value changes according to the search state like decision trees. This is beneficial in many cases because the evaluation value can be optimized to each search state. But sometimes it can be demerit in the different search states like in parallel search environment or something like that. Indeed, Oderman and Simon stated that LBD is relative to the current search state of each solver, and a good clause for one state may not be good for others, another or like that. So our key idea is to have a such independent metric for the closed sharing. To do that, we need to have some static or the fixed value cross evaluation metric across any such state. And for that fixed value metric, our idea is to use the structural feature of the graph of such problem. And particularly, we apply the average external edge weight. That is a measure we proposed in our previous study for the sequential cross deletion method. And our parallel cross sharing strategy is named PAX. And this AEW will be introduced in the following slide. The reason why we came to an idea to use the structural features for the static and fixed value is that the graph structure is one of the hypothetical explanation of the SAT solver's efficiency. Many structural features and measures has been proposed, like the community or self-similarity or these things. And the differences of these values between the random instances and application instances has been known. Also, these values are known to correlate to the runtime of the search. In addition, the learning is the relationship between learning and these structural values are also known. And usually, adding the learning or adding the learned clauses to the original structure is said to be destroy the original application structures. And also, our previous year's post presentation showed that there is a relationship between the structure quality of the learned clauses and the degree of changes of by adding the learned clauses in the structures. In 2018, Simon Jamri and David Michel proposed to use the between centrality, one of the structural feature, to improve the heuristics. And we think that they showed the potential to improve the heuristics by using the structural features. So before moving to the proposal, let me touch some preliminary experiment result. We conducted some preliminary experiments to answer the question that is LBD effective for parallel search clause evaluation. Our hypothetical answer is no. That is because LBD value depends on the search state, like decision tree, and each parallel worker should have the different search state. So the LBD value may not be appropriate to each workers after the sharing of the clauses. To verify that, we conducted and set up an experiment using the portfolio type parallel search solver and compare the usefulness of shared learned clauses and obtained learned clauses. Regarding the clause sharing, consider the master and worker type parallel architecture, and each worker obtains their learned clauses, and each worker selects some clauses that should be beneficial for other workers, like orange ones. And they send them to the master worker and master distribute to each workers. And each worker use these learned clauses to prune their such spaces. To do that, each worker have some criteria to decide which clause to share. And our first preliminary experiment is to check the performance of the different sharing criteria. We set up some criteria like as a baseline LBD less than or equal to 2. And we set up some size and no sharing solvers. And the experimental setup is like this, 5,000 seconds using 1 year benchmark and like this. So here, this table shows the result. As you can see, the number of them indicates the number of instances solved. As you can see, the size outperformed the LBD, particularly less than or equal to 1 or less than or equal to 8 outperformed LBD much. So from this result, we thought that LBD may not be the appropriate method for the sharing to decide the clauses for sharing. And the next experiments was conducted to check whether the shared land clauses are useful for other workers. To define the usefulness, we set up this used % for the set of clauses. Given a land clause, this clause has a Boolean value, and it gets 1 if that clause is referred in conflict analysis at least once. And given a set of land clauses, this used percentage indicates the percentage of used clauses of this set of clauses. And we compared used percentage between shared land clauses and land-to-land clauses, or the land clauses which workers obtain by itself. And this result shows a result. A yellow line shows the land clauses obtained by the worker itself. As you can see, a higher used percentage decreases in accordance with LBD value increases. Blue line indicates the used percentage of the shared or imported land clauses. And the percentage itself is much lower than yellow line. And also, it does not depend on the LBD, or the dependency is much less than the yellow one. This result is just shows just one instance as an example. So here is a 400 instances distribution as a used percentage. And left one shows imported, the shared land clauses used percentage. And the right one is average land clauses used percentage. As you can see, the higher used percentage in the land clauses, but less used percentage in the shared land clauses. So this result indicates that LBD is effective and useful within a worker and within a same such context and such state, but it does not in the case of across the workers, beyond the workers. So finally, my proposal and evaluation. So because LBD may not be appropriate for the clause sharing, our idea is to have such independent metric. And one idea is to use the size, because size is obviously fixed, and it shows the same value across any such state. But in this study, we came to an idea to use the average external edge weight, which we proposed in our previous study. And average external edge weight is the value, shows the value of a land clause in the graph structure. What I mean is the value is defined like this. It shows the average edge weight, between the nodes of a land clause and outside of the land clause. Here is an example in the left bottom. Consider the graph from the CNF, and this is a subgraph. And blue nodes are the variables in the land clause, and white nodes are the adjacent nodes in the graph. And the value of average external edge weight, AEW, calculates the this edge weight between the blue node and white node. So heavier weight indicates a larger AEW value, and larger AEW value means a better land clause quality. And because of this definition, we assume that what AEW value measure is the possibility of propagation, because heavier edge indicates that these nodes belongs to the short or multiple clauses, and these nodes have higher possibility of unit clauses and propagations. So using that average external edge weight metric, we implemented and modified the base solvers to implement the PAX method. added the calculation of AEW value for any clauses, and the sorted of the clauses are done by according to the value of AEW first, and if equivalent LBD, then if equivalent size. Here is our experimental setup. We compared the performance of solvers by measuring the number of instances solved and part 2 scores. The benchmark set we used was 1,200 instances from 3 years SAT competition, and time limit was 5,000 seconds. And the number of parallelization is 16. And as a base solver, we used the ParkSat RS, and we modified to implement the AEW on top of this ParkSat RS. This table shows the result. From the number of instances perspective, our proposal outperformed the LBD, and also the size, the best result of the size. And the improvement in the number of instances plus 4%, but the part 2 score improvement is plus 12%. Particularly, the number of unsat improvement was much bigger than the satisfiable instances. We assume that this is because the parallel SAT solver could share the kind of universally useful round clauses by measuring the such independent metric. So let me conclude my presentation. Through the preliminary experiments, we showed the opportunity to improve the clause evaluation in the parallel clause sharing task, and to have such independent metric, we proposed a new clause sharing strategy, PAX, using the average external edge weight, AEW. And AEW is a static evaluation metric using the graph structure of the SAT program. And performance evaluation experiments indicate that the PAX is more effective than LBD. As a future work, we need to optimize the implementation, such as parameters and data structure of the graph. Also, we are willing to find another structural measures for the clause evaluation. Also, we are now doing some, based on the idea of new evaluation metric based on the propagation possibility. That's all for my presentation. Thank you.
Thank you. We have plenty of time for questions.
Thank you for the nice talk. So first of all, I really like that you also made this observation that the LBD value is really a weird metric in parallel clause sharing. I don't know if you heard my talk on Tuesday, where I said something similar. So I think it's good if we come to terms with that and try alternative strategies there. I have two questions. The first one. Did I understood correctly that you used up to 16 cores of a 64-core machine?
16 workers for the parallelization, but we used a 64 core. So at the same time, for max for simultaneous experiments work.
So each worker has 4 cores, or
no? Each worker has 16 cores. Each worker, I mean, each parallel solver has 16 cores.
And then you used how many solvers? Like what's the total number of cores you use at once?
4 instances are solved at the same time.
I don't understand. Like how many cores you used at once for one formula? Just for
one formula, 16.
Okay, so you use 16 cores for one. Okay, because I wondered if like how it scales if you increase the number of cores. But you didn't do experiments on that?
Sorry, I didn't.
Okay, because 16 I think is maybe still small for shared memory. You could test maybe 64 or something. And you compared against sharing clauses of size up to 8, which is like this kind of fixed quality metric. And yeah, so I would maybe consider. So what I'm doing, for example, is that each thread exports its clauses absolutely liberally, so up to clause length of 60 or something. But then you use then you just make a cutoff just of the clauses you've gathered, right, across all of your workers, and then you use the best ones. And I think that is a strategy that also works very well, and this maybe could or should be compared against. Sorry, one last question, but there's a 2020 SAT paper by Balad and others based on the community structure and clause sharing based on that. So could you maybe comment what's the difference here with your approach?
Oh, yes, they use the community structure, combining LBD and community structure, I remember. And so actually, in my previous research, we tested the, in our previous research, we compared average external H weight and community number of communities and tree weights or these some structural features. And we found that ABW, this metric shows a very strong correlation to the value of LBD. So we decided to use this instead of number of.
Okay, but there was this, like they had one metric that was also based on the community structure, right? And they also used that in an isolated manner. So what's the difference between that metric and your metric?
You can my metric. What do you mean? Sorry.
Sorry.
The differences of the number of community and this one.
Between the community measure that was proposed in 2020, I mean.
Yes. So they proposed to use the number of community, and this AEW measures the weight of the edge, not the number of community.
Ah, okay. Yes. Okay. Thank you.
Yeah, the perfect slide. So you need to recompute this AEW for every exported clause, right? And this has a quadratic kind of thing in it. So do you compute these edges and their weights statically upfront, or is this done dynamically for the current formula, including the learned clauses?
Okay. Before the search started, we construct the graph, and then no adding the round clauses during the search.
But this is still sort of like a quadratic matrix. So if you have 10 million variables, it's 10 million times 10 million. You have to pre-compute, or how does this?
Yes. Some, not sometimes, but not sometimes, but for some instances, the construction of the graph spend many times, and these instances were timed out for the 5,000 seconds.
Yep. Thanks.
Other questions? Okay, if not, we can end this section, and I think we have more time for the coffee break. Okay. Thank you.
And of course, it goes without saying that if you want to use any meeting room, if you want to have any discussions, there are whiteboards, there are markers. Please get in touch with Abhishek and his team. Next session will be the last session, of course, the most awaited solver results.